Okay, so today we'll start with our fifth practical, which is to study speed control of DC shunt motor using armature voltage and field current control method. So there are two methods of controlling speed of DC shunt motor. One is armature voltage and second is field current. So both these methods you have to use. Then measure RPM, and RPM means speed you have to measure, and plot the graph of speed versus armature voltage in one experiment, and in second speed versus field current. So these two experiments we have to perform. So this is the practical number 1 which you have to perform. Otherwise, first 4 practicals are the simulations. So we have simulated on the 2 simulation softwares. We have tried to simulate them on 2, rather there are 3. So on 3 softwares we have tried to simulate them, and these practicals you have to perform in the lab. So today we'll perform it on the virtual lab, which are developed by the Ministry of Human Resource, and they are available in IITs for freely use to all the engineering students amongst India. Okay. So this DC shunt motor practical 1, the aim is to control the speed of DC motor using 2 methods. One is armature voltage and another is field current control. You have to measure the speed, and then you have to plot the graph of speed versus armature voltage in one case, and in another case speed versus field current. So what will be outcome of this? So outcome of this is you will be able to understand speed control characteristics of DC motors. The theory of DC motors, there is one unit in your syllabus, 4th unit of DC motor. Whole unit is there. So in that we'll see detailed working, construction, principle, various types of DC motors, numericals, equations, and speed control methods, and starters. So all these we are, and applications. So all these we are going to see in that 4th unit. But just to perform the practical, whatever basic knowledge is required, we'll discuss that. Okay. So after performing the practical, your ability to understand the speed control techniques for DC shunt motor will be enhanced. So I'll show you first simulation how this DC motor works. Okay, so I'll stop sharing this screen, and I'll share another screen. Okay. So is it visible to you? Yes, Avi? Is the new screen visible to you? Okay. So DC motor principle is, whenever in one line you can state that whenever a current carrying conductor is placed in a magnetic field, it experiences a force. And the direction of force is given by Fleming's left hand rule. Then you can see in this picture, 2 magnets are there, permanent magnets, south pole and the north pole. These 2 magnets are shown, and there is one armature conductor. So this is an armature which is placed in this 2 magnets, north and south pole, and that armature, square armature, it is connected to a battery, DC battery, through this commutator and brush arrangement. Now the current will flow. This is a small video. I will show you, and then we'll discuss What is that?
At that position, we can determine mechanical force with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one to another. So if forefinger is aligned in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of the current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is aligned in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of the current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces tends to rotate in clockwise direction. From that explanation we can come to conclusion that here in this model we can see that whichever conductor comes near South Pole experience upward mechanical force, and near North Pole downward mechanical force. And do this continuously forces mechanical turn rotate, even if battery is not connected. Particularly DC motor rotates at the same principle like this elementary model. Instead of single turn in DC motor, we have mountain turns on major coil. And instead of 2 poles, there is number of poles installed.
Okay, so I hope you have understood the principle of this DC motor. Whenever the conductor is placed near South Pole, it is experiencing a force in upward direction, whereas the conductor which is placed to North Pole, near North Pole, will experience a force in downward direction. So it produces, there are 2 forces acting on this conductor. One is in upward direction, another is in downward direction. So couple of force in opposite direction. So they produce a torque and the motor rotates in a particular direction. So this is the basic, simple basic principle of DC motor. Now we'll move to our discussion. I hope you have understood what is the principle of DC motor. Now again we'll come to our presentation. Yes, is second screen visible to you?
Yes, sir.
So what you have understood in this is, I think there are 2 windings, or you can say one armature winding is there and another 2 permanent magnets are there. So in case of DC motors, which is we want to operate a shunt motor. So DC shunt motor, series motor, or separately excited DC motor, in these types of DC motors, field winding is provided. So this field winding, you can see in this picture, one field coil is there and here IF is written. So this field winding is serving the purpose of the permanent magnets. So the permanent magnets and an armature coil. So that you have seen in the picture. So instead of permanent magnets, this field winding is there. So this field winding is providing the task of permanent magnets. Okay, so it is providing the flux, and the armature coil is this. So that second coil which is shown, it is this armature winding or armature coil. So these 2 coils are there. So for this armature winding, we are applying here armature voltage VA. A suffix stands for armature. So armature voltage we are applying. This is LA and RA. So these are the inductance and resistance of this armature winding. As it is a winding, what do you mean by winding? Winding is nothing but it is a coil. So it is a coil. So coil means a simple copper wire. You are winding it. So when you are winding it, it will have a inductance. And since the wire is made up of copper, it will have its own resistance. So this particular winding will have resistance and inductance. So they are shown here along with this armature. So this is the armature and this is the shaft of that particular motor. So this is symbolic representation of DC motor. This is actually separately excited because this is the shunt field winding which is connected separately. In shunt type, this is connected across this armature winding. So that is the shunt motor. So whatever it may be, we are interested in few equations. So all these we'll see in detail in theory, but here you will require this VA. If you will apply KVL to this particular loop, you can find that VA is equal to this EG plus IARA. IA is the current flowing through this armature. So IARA drop. So VA minus IARA will be equal to this EG. What is this EG? EG, or usually it is referred as EB even. In few books you may find it as EG, or in few books you may find it as EB. So that term is the back EMF. So back EMF means the generated EMF due to the speed. So since the motor is rotating, that produces again some EMF, and that is exactly in opposite to that of the voltage which is applied across this armature. So this VA minus IARA will be equal to EB, back EMF. So this is one equation. Then this back EMF is also proportional to phi into speed, where this phi is nothing but the flux produced by this field winding. So this phi is proportional to IF, that is the field current flowing through this field winding. And the torque developed, that torque is proportional to phi into IA. Means this IA is the armature current and phi is proportional to IF. Means torque is ultimately proportional to IA into IF. So torque is basically depending on this armature current as well as on field current. Now this some rearrangement of these equations you can substitute, and you can find this omega or speed, that is equal to VA minus IARA divided by phi, means K into phi. That is the proportionality constant, or this phi is proportional to IF, so you can substitute that IF. So omega is equal to, means speed is proportional to VA minus IARA divided by IF. So that means speed is directly proportional to VA, that is armature voltage, and speed is inversely proportional to IF. And these two methods we want to implement for speed control, right? So we have got this equation, omega or speed, which is proportional to VA minus IARA drop, whereas RA is very small, so this drop you can neglect. So this speed is directly proportional to VA, that is the applied voltage across armature, and it is inversely proportional to IF. Speed is inversely proportional, 1 upon IF. It is proportional to 1 upon IF, means inversely proportional. So the motor speed can be varied by armature voltage and field current. So there are two methods. Now both these methods are very important, because in first method you can change the armature voltage and you can achieve the variation in speed from 0 to rated speed. So rated speed, what do you mean by rated speed? It is the speed at which or that corresponds to the rated armature voltage, rated field current and rated armature current. That is known as the rated or base speed. And all these rated values, they are mentioned on the motor. So there is a flap on a motor, and on that flap it is mentioned what is the rated voltage, what is the rated current, armature and field, and what is the rated speed. So usually 1400 RPM is the rated speed of the motor which is available in lab, or it may be twice of that, 3000. Okay, so that is the rated speed. So with variation in VA, means VA you can change from 0 to some value, let us say 220 volts. So from 0 to 220, if you are changing the value of armature voltage, then your speed will change from 0 to the rated speed, that is 1400 RPM, right? And opposite is the case of field current. As you can see here, speed is directly proportional to VA. So as VA is increasing, speed will increase, and for IF it is inversely proportional. So if you are reducing the value of field current, then the speed will increase. And this method, usually it is referred as a field weakening method. Why it is field weakening? Because we are weakening the current or field, or we are weakening means we are reducing the value of current so that the flux linkages will weaken or they will be brought down. So that is the field current control method. And by reducing the field current, you are reducing the field flux linkage. So as you are reducing the field flux linkages, the speed will be more than the rated speed. So that means by field control method, you can go beyond 1400 RPM. So as you are reducing the value of IF, you will find that the speed will increase more than beyond 1400. So 1400, 1500, 1600, maybe up to 3000 or 2000. Okay. So the difference you got between these two methods, one is armature voltage control. In armature voltage control, by controlling the voltage from, increasing the voltage from 0 to maximum, you can increase the speed from 0 to rated speed, that is 1400. So maybe 0, 100, 200, 500, 800 and then 1400. Okay, so this will be the variation if you are varying the armature voltage. If you are weakening the field current, that means you are reducing the value of field current. So initially it was 1 ampere, you may make it as 0.8 ampere, then 0.7 ampere, 0.6 ampere, 0.2 ampere and so on. So as you are reducing or weakening the field current, your speed of that DC motor, shunt motor, will increase beyond the rated value. That means it will increase from, it will start from 1400, say at 1 ampere, it is at 1400. So if you will make it as 0.8 ampere, then it will increase to say 15 or 1600. If you are reducing further to 0.5 ampere, let us say, so it may increase to 1800 or 2000 RPM and so on and so forth. So got this difference? Yes? Avi?
Yes, sir.
So one more thing I want to tell you, that the armature voltage control, it is, the nomenclature is armature voltage control and not armature current control. Okay, and field current control, not field voltage control. So you keep in mind these things. It is armature voltage control and field current control. Now, this armature voltage control, it is also referred as a constant torque operation, because torque is directly proportional to phi into Ia and phi is proportional to If, field current. That means torque is proportional to Ia as well as If. Now in this armature voltage control method, we are keeping field current to a constant value, armature current to a constant value, so your torque will remain constant. That's why it is a constant torque operation. And by varying the value of VA, you are changing the speed. So that's why it is also referred as a constant torque operation with a variable speed. And in second case, field current control method, as torque is proportional to Ia as well as If, and you are varying If, so that means on the cost of torque, you are changing the speed. Meaning is your torque will start reducing as you are reducing the value of If. As If is reduced, so torque is proportional to Ia into If. If you are reducing, so as you are reducing If, your torque will reduce, but your speed will increase. So on the cost of torque, you are increasing the value of speed. That's why this is also referred as a constant horsepower operation. Okay, so I hope it is clear to you what is armature voltage control and field voltage control. Yes, in this diagram you can see, in case of armature voltage control, on left side, this at the middle 100, it is shown is the rated speed. Okay, that is the 100% your rated speed. That is, let us say in our case was 1400 RPM. So this 1400 RPM is the rated speed, and below that you can operate at a constant field current. Armature voltage you can vary, and your torque will vary, your power will vary, and your speed will increase. Right? So this is a constant torque operation, and this is constant power operation, that is the field current control, in which you are reducing field current, your armature voltage is remaining constant, so the power is constant, so it is constant power operation, and on the cost of torque. So torque is reducing, whereas speed is increasing. And in second case, that is armature voltage control, your torque is constant and speed is increasing with voltage. So I hope your ideas are clear. Then we'll go for circuit of armature control method. So in armature control method, as its name suggests, we are connecting one variable resistance in series with an armature. So this is the armature of the DC motor. In series with that, we are connecting here a variable resistor. So we can change the value of this resistance so that we can change this supply voltage applied to this particular armature winding. So VA will be controlled. So as VA is controlled, VA, that equation is there, omega equal to, means speed is proportional to VA minus IARA by KA phi or KA into IF. So depending on the variation of voltage, we can change the speed. That is the armature control method. And second is the flux control method, in which the field winding, this armature winding, it is connected directly to supply, and for field winding, now we are changing its value of current which is flowing through this armature, field winding, with the help of this variable resistance or variable potentiometer arrangement. And by varying this field current, we are changing the speed, because that speed is inversely proportional to this IF. So this is the circuit which we'll be using, and practically this is the circuit diagram which we are using for performing the practical. So here is the supply voltage, 230 volt DC supply. As it is a DC motor, we are using DC supply voltage. This is the field winding, and this is the armature winding as shown. Now we want to measure armature field current. So field current value, if we want to measure field current, that's why we have connected one ammeter over here, and this is the field winding. Along with that, we have connected a variable resistance in series with this field winding. Okay, so this resistance we can vary, and we can ultimately change or vary the field current value, and that value we can read it on this ammeter. And for this armature winding, we want to measure armature voltage. So we have connected here a voltmeter across this armature, so that voltmeter will read the voltage value across the armature, voltage applied across armature, and that we can vary by connecting a variable potentiometer or variable resistance in series with this. So by varying this value of resistance, we can change the applied voltage across this armature of the motor. So both the experiments we can perform. That's why on the same setup, that's why we have shown here two potentiometers. So for first method, if we want to change armature voltage, we'll keep this potentiometer at a particular value, so that field current will be having a constant value at a particular value, and will go on varying this potentiometer, which is connected with the in series with the armature. So we are varying armature voltage at a constant field current, and will get variable speed that you can measure with the help of tachometer. Tachometers are the meters which are measuring speed in RPM. So tachometers are of two types. One is analog tachometer and another is digital tachometer. So analog tachometer you can directly connect to shaft of that DC motor, and the reading of that will be available on the dial. So that is one, and another is the digital, which is non-contact type. So instead of connecting it to the shaft of DC motor, by remote controlling, you can measure the speed. So in that, what is done is usually a white tape is pasted on the shaft of the DC motor, and this remotely controlled tachometer, it is radiating the IR light, infrared radiation, and that infrared radiation will detect that particular white spot or white stick, and that will be detected and the speed will be measured. So that is the non-contact type of tachometer which measures speed. So in both the cases, you can measure the speed. After measuring the speed, you can note down the readings for different values of voltage. You can measure the speed. You can make note of voltage versus speed, and then you can plot a graph of armature voltage variation and speed of DC motor. So that is one part of experiment. And in second part of experiment, you are varying the field current. So by keeping armature voltage to a constant value, armature current to a constant value, that means this second potentiometer which is connected in armature, that you will keep it at a particular value, so that this will be constant, and you are varying this field winding potentiometer, so that your field current will vary, and after with variation in field current, again your speed will vary. That speed you can measure with the help of tachometer, and you prepare a table which will read the voltage, current, field current and speed. So these you can plot a graph. So I think we are moving out of time, so we'll move fast. So usually this is the circuit diagram in which one starter is shown. So what is this use of this starter? So as you know, the voltage equation VA, armature voltage, it is equal to EB plus IARA. From this, by rearranging these terms, you can find the expression of IA. So IA will be equal to VA minus EB or EG divided by RA. That is resistance, armature resistance. So initially, the value of EB is the back EMF which is proportional to speed. Initially, speed of the motor is 0. So if motor speed is 0, EB is 0. And VA, if you are applying suddenly 220 volts, RA value, usually it is very small. In case of shunt motor, it is usually of 1 ohm. So whatever 220 volt you are applying, divided by 1 ohm resistance, as EB is 0, so it will lead to a IA to a very high value. So IA is very high. So as torque is proportional to IA, that means speed is also proportional to IA. So your speed will immediately boost, and it may cause damage, mechanical damage to the motor. Your shaft of motor may get damaged, or bearings in the motor may get damaged. So that will give you damage in the mechanical damage in the motor. So in order to avoid that, what you have to do, instead of applying sudden 230 volt DC, we are applying it gradually. So how to apply it gradually? So that is with the help of this starter. So starters are nothing but it is a combination of resistance, just like your fan speed regulator. You are changing the speed of fan by regulator. So the same technique is used in this starters. Initially, the resistance of the starter is kept high, so that the applied voltage will be very small, and then gradually that value of resistance is reduced, so that the applied voltage will start increasing, and sudden voltage will not appear, which will not cause sudden rise in the current IA, and which will not give the mechanical damage. So this is the starter. In modern type of drives, we are using the electronic control, power electronic control. So we have got SCRs, silicon control rectifiers, MOSFETs, so IGBTs. So we can control the voltage with the help of control converters. And with the help of these control converters, you can apply a gradual increase in voltage from 0 volt to maximum volt. And that is referred as a soft start, because you are applying the voltage, applied voltage is gradually increasing. So you are starting the motor with a slow speed. Otherwise, if initial current is very high, it will start with a high current. So I hope you understood the concept of this starter, soft start. I think we are running out of time. I'll stop this meeting. I'll again float the meeting, because we have not completed the practical yet. So we'll complete it, and then we'll stop today's lecture. Okay. So within 15 minutes, because I'll require 15 minutes.